Okay, so let's continue our discussion related to combinational circuit design. And in the last lecture, we were seeing that if you have to design a digital circuit block, the design flows according to this particular approach. So given a system that you want to design, so you want to solve a problem and you want to design a digital system to solve that particular problem. So from the description, what we do is we get a truth table. So once you understand the system, you know what the input variables are, you know what the output variables are, and the relationship between the output and the input is captured in the form of a truth table. And once you have a truth table, then we said that we can convert the truth table into a Boolean expression. And then what we do is, since we have to eventually implement a circuit, we would like the expression to be as simple as possible. So we minimize the Boolean expression. We try to make it as simple as possible. And then we convert it into a network of gates. And these network of gates then can be converted into a network of transistors. And we get a digital circuit that would perform the function that this particular system requires here. So for example, so the first step in doing that is to identify what the inputs to the system are and what the output of the system is. And then capture the relationship between input and output in the form of a truth table here, convert it into a Boolean expression, minimize the Boolean expression, then map it onto a network of gates. And we have not shown here, each one of those gates is implemented using, let's say, N-type and P-type MOSFETs. And then you get a digital circuit that would perform the function that is intended in this particular functional relationship here. All right, so we saw earlier that minimization, and we see from here minimization is a very important step here. So the Boolean expression that we get from the truth table is not the simplest possible expression that we can get here. And one should not directly take the Boolean expression and map it onto the gates here, because then the circuit would be unnecessarily complex. So an important step is to take the Boolean expression and minimize it. And in that context, we said that there's a way of representing the information that is there in the truth table such that we can easily apply the principle on which the minimization is based here. So so let's look at that, what that representation is. So for example, if you have a function of two variables, x and y here, and so x and y can take these possible values 0, 0, 0, 1, 1, 0, 1, 1, and each one of them is a minterm, right? X bar, y bar, x bar y, and so on and so forth. So this information we can represent it in this sort of a matrix form here, with x variable taking values 0 and 1 and y taking 0 and 1 here. So 0, 0 will correspond to this particular minterm. 0, 1 will correspond to M1, 1, 0 will correspond to M2, and 1, 1 will correspond to M3. All right, so so the idea is that the same information that is there in the truth table is now represented in this matrix form. So for example, this is a truth table here, and it's a function of two variables. So we put x here, we put y here, and x can take again 0 and 1, y can take 0 and 1 here. And so the idea is now when x takes 0, 0, so when x is 0, 0, the output is 0 here. So we put in this particular box here 0. When x is 0 and y is 1 here, so it is this particular box here. X is 0, y is 1. And when x is 0 and y is 1, it is 1 here. So we put a 1 here. And similarly, when x is 1, so x is 1, y is 0 here, the value of the function is 1 here. And when x is 1, 1, the value of the function is 0 here. Right? So it's the same truth table, but we represent it in this matrix form here. And we'll see that this particular representation will help us in minimization. All right, so suppose we are given a two variable function here, f2, two variable function, and it has these minterms 0, 2, and 3. So we can represent it two variables. So we x and y here, 0, 1 here. We know, what does it mean? That this particular function, when we write it like 0 here, this particular function has a value 1 when x and y are both 0, 0. So we put it 1 here. Also, this function is 1 when x and y are 1, 0 here. 2 means 1, 0 here. So x and y are 1, 0, so 1 and 0 here. So we put it here. And it's also 1 when x and y are 3. So 3 is 1, 1. So 1 and 1 here. So we put a 1 here. Right, so we can, given a Boolean expression like this here, we can map it onto a representation which we call as a Kmap. K stands for Carnot, the person who first proposed this kind of a representation. All right, so for example, or other way around also, suppose we give you a Kmap like this here, and we ask you for a Boolean expression. So what we do is we find out when, so these values inside the box, they represent when are the function equal to 1. So the function is 1 when x is 0, y is 0 here. So there has to be a term called x bar, y bar. X bar, y bar. And it's also 1 when x is equal to 1 and y equal to 1. So that's why we put x, y here. So we can go back and forth. We can go from a Boolean expression to a Kmap representation. And we can go from a Kmap representation to a Boolean expression here. Okay, so let's look at a 3-variable Kmap here. So 3-variable Kmap, there are 3 variables x, y, z, and we know that the possible values are 0, 0, and 1, 0, 0 here and 1, 1, 1 here. So basically from 0 to 7. And so we can represent it in this form. X takes value 0 and 1 here, and y and z, they take value 0, 0, 0, 1, 1, 1, and 1, 0. Now note that we have written in a specific manner here, 0, 0, and then 0, 1. The next value that we take, for example, yz we know can take 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, we could have put here 1, 1, we could have put here 1, 0. But there's a definite order in which we have put here. 0, 0, 0, 1, and then 1, 1, and 1, 0. So note that the basic order is that as you go from one box to the next box here, there's only one bit change here. 0, 0 to 0, 1, there's only one bit change here. Similarly, when you go from 0, 1 to 1, 1, there's only a 1 bit change here. And 1, 1 to 1, 0, there's only a 1 bit change here. And that 1 bit change is important because when you represent it like this, we are going to apply a principle called x plus x bar equal to 1 here. So that's why we are representing it like this. Here, similarly, 0 and 1, so there's a 1 bit change here. So anyway, a 3-variable function could be represented in this form, x, y, z here, and these are the values here. So for example, if you have a truth table like this, so we can represent it in a Kmap like this here. So 0, 0, 0 here, this is 0, 0 here, 0 here, 0 when x is 0, yz is 0, 1, when x is 0, yz is 0, 1, so we put 1 here. Similarly, when x is 0, y is 1, 0, 1, 0, so it is 0 here, and like that we can fill it up. We can fill up the Kmap here. All right, so it's a same representation. The truth table representation is represented in this Kmap kind of a representation here. And all right, and same thing. So if we are given a function like this, we can map it onto a Boolean expression here. So all we need to do is look at where do we have ones here. So we have a 1 here, and this stands for x is 0, y and z is 0 here. So it becomes x bar, y bar, z bar. Then we have 1 here, so that stands for x is 0 here, y and z are 1, 1, so x bar, y, z here. Similarly, we have a 1 here, so that stands for x is 1, and we have 1 here, so y is 0 and z is 1, so x, y bar, z here. And then we have x is 1, y, z are 1, 1, so we have x, y, z here. Right, so we can go from a Kmap to a Boolean expression. Okay, so let's look at a 4-variable Kmap representation. So when we have 4 variables, say w, x, y, z here, so they can take values of 0, 0, 0, 2 all the way to 1, 1, 1, 1. And so 1, 1, 1, 1 is nothing but 15, so you can go from 0 to 15. And we can represent it in this form here. We can have wx as one set of pair of variables here, and yz is the other pair of variables. Yz is here, wx. So the first 2 bits wx here, and the next 2 bits, next 2 variables here are yz here. Yz can take 0, 0, 0, 1, 1, 1, 1, 0. Note the 1 bit change here as we write it. Similarly, wx 0, 0, 0, 1, only 1 bit change, 0, 1 to 1, 1, and 1, 0 here. And again, now we can fill it up depending on the function that we have here. So we have a function like this, and so we can, given a truth table, we can fill this up, and given the Kmap here, we can write the Boolean expression by again going to the boxes where you have only 1 and writing the corresponding term. So 0, 0, 0, 0. So w bar, x bar, y bar, z bar. So wherever you have a 0, that is complement W bar and X bar, right? And so like that, for example, this term here, this term would be Wx is 1, 0. So W is Wx bar here, Wx bar, and 0, 0 means Y bar, Z bar here. All right, so we know now that Kmap is an alternative representation of a Boolean expression or a truth table kind of a representation here. So let's look at how this particular representation is useful for minimization. So let's say we have a function, two-variable function, and the function has min term 2 and 3. So 2 is 1, 0 here, this is 2, and 3 is x is 1, y is 1, so 1, 1 here, right? So we put 1, 1 here, and the rest of the terms are 0. Okay, so when 2 and 3 are given, it's implied here that the rest of the terms are 0 here. So we want to minimize it. And the minimization, so note that so this first term can be written as x, y bar. This is x, y bar here, so x, y bar here. The second term can be written as x, y here. Right, so our minimization was based on taking the common variables out. We know that we can take x out and we get y plus y bar. And so what we are doing is, if you look at it, when you take x out, you're combining the two terms together. And this first term corresponds to this first box here. The second term corresponds to the second term here. So this combining thing, we can represent it by this encircling here. So when you encircle the two, what you're saying is you're combining the two terms here. Each box represents a min term here. So you're combining the two term here. And when you combine them, what happens is, note that between these two terms, this one is common. This x is common between these two terms in a row here. And what is changing is y. Y is changing 0 here and 1 here. So y is 0 here and 1 here. So when you combine, when you encircle and combine the terms, what happens is the term which is common to both of them, that remains, and the term which is changing, that disappears. F is equal to x here. So y is changing, y is 0 and 1 is changing here. And so that disappears because of y plus y bar equal to 1 here. And what is common x remains here. So this taking x common out, applying this particular principle y plus y bar here, can be done on the Kmap representation by looking at two neighboring ones and combining them like this here. Okay. And so combine terms which differ in only one bit position. So when you combine two terms, what you want to do is apply this principle y plus y bar. So you want the two terms that you're combining, you want them to differ in only one bit. That one bit is changing, that one variable is changing from 0 and 1. And that's why you can apply y plus y bar equal to 1 here. All right, so let's see this here. Okay, so this is another a Boolean expression. And I'm sure you can write down what the Boolean expression is by looking at the terms for which you have a 1 here. So this one, the first one is x is 0, y is 1, so it is x bar y. The second one, x is 1 and y is 1, so you write xy here. So here, if you didn't have a Kmap kind of a representation, you would have taken y out here. You would have taken y out here and would have gotten x plus x bar, and that's equal to 1, and it would have become f equal to 1 here. So when you're doing that, you're combining the two terms, right? Again, you're combining these two terms here. You're combining, so when we encircle it, what we mean is that the two terms are being combined together. And when they combine together, what is common between these two terms? The common is y here. Because note that for both of these terms, there is a y here, 1 here. 1 is common. When you look at a column, this column is common here, 1. And what is changing is, well, for this term, x is 0. For this term, x is 1. So what is changing disappears when you combine them, right? X plus x bar. So you get f equal to y here. So this combining terms and taking the common factor out and applying this principle x plus x bar, well, instead of doing it on the Boolean expression, we can do it on the Kmap. Right? So let's see. Can we do this? In this case, well, we can combine them together here, these two terms. Note that when you combine them together, what you're looking for is that there should be only, the only thing that should be changing is one variable. And that one variable change in this case should be, for example, when we combine these two together, y is common, y is 0 here, but x is changing. right? So when we combine them together, what are we going to get? Well, what is changing will disappear because it will end up as x plus x bar, right? And so what you'll end up with is y is common between them, and so you'll end up f equal to y bar because y is 0 here. Okay, and you can, so similarly, for example, if we have these two ones here, well, we can combine them together here. And in this case, well, what will be the value of the function here? So when you combine them together, x is constant while y is changing, so that will go away. So we'll end up with y plus y bar, and so f will be equal to x bar because x is 0 here, right? So we have two terms, we combine them together into a simpler term, f is equal to x bar here. So we can see that, instead of looking at a Boolean expression and seeing which terms can we combine, well, we can do it visually because we have all the data in a visual form, and we can see where are the neighboring ones, and we can combine them together here. All right, so the principle that we are using is x plus x bar equal to 1. And we'll also see that we also use this principle that once you combine one term with another, it doesn't mean that particular term is lost. You can combine it with another term as well. And that is based on this particular principle here. So let's look at this particular function, 0 to 3 here. So here, well, we can combine these two together, right? So note that this particular function is xy bar xy and x bar y here. So when you combine them together, well, you're combining the first two terms, right? You're combining the first two terms and you're getting, note that when you combine them together, what will happen is y will disappear, you'll get only x, right? So that's why we get x here. But you have another term left here, right? This another term is x bar y. So another term is left. So how do we simplify? Well, what we are saying is this particular principle, it says that when you combine one term with another, let's say you combine this term with this one here, it doesn't mean that this particular term is no longer available. What we are saying is x plus x equal to x. So this is also available. You can make another copy of it. You can add another x to it, to our expression, and nothing will change. So which means that there's also a possibility of taking this one and combining it with this one here, right? And that when you combine it together, you'll get even simpler one, right? So what we are saying is you can add another term of this kind here and combine it together, and you get x plus y. So the first circle is only x. The second encirclement that you've done is y here, right? So f is equal to x plus y here. So the function becomes x plus y here. So the idea is that you have to, when you fill a Kmap, you will have certain number of ones that are there. So the idea is to cover all the ones that are there in as simple a manner as possible here. Okay, so we covered this in this particular manner, these two ones, we combined them together. So we covered these ones using x here. But then this one was left. And if we just leave it alone, then we would have gotten a term x bar y. But we are saying you can combine this with this also here. And then you get another term. Each encirclement represents a term. You get a term which is basically equal to y. Right? So the simplified function is f is equal to x plus y. Okay, so the idea is to cover all the ones with as few and as simple terms as possible. Note that every time you combine something with one term with the other term, you get a simpler term, because when combining, the variable which is changing, it disappears here through this particular principle, y plus y bar. It becomes y plus y bar, so this is equal to 1. And so when you combine them, two terms, you get one term. And so there are two benefits. Note that when you combine the two terms, you get one term. So that's the first benefit. You're getting a single term. And the second one is the term becomes simpler. So when you combine them, it has only x in it. It doesn't have a y in it here. So it becomes simpler also. And so all the ones that are there here, you would like to cover all the ones through these kinds of combinations that are there here. All right. So this will become clearer as we proceed with more examples here. So let's take a 3-variable function here. So now, so imagine that you have a function, you have a truth table, and we have mapped it into a 3-variable Kmap here. So the variables are x, y, z. X goes 0, 1 here, 0, 0, 0, 1, 1, 1, 1, 0 here. All right, so how can we simplify? Well, so this whole thing has 4 terms here. So these are the 4 terms here. So we have written it out. Well, one combination that we see is here. This 1 and 1, we can combine them together. Why is it that we can combine them together? So note that x is common between both of them. And so x common, so you will take it out. And if we look at these two terms, 0, 1 and 1, 1. So between these two terms, 0, 1 and 1, 1, note that z is also common. So which means when you're combining them, you will take x and z out. And you will be left with only y, which will be changing from 0 to 1. And therefore, when you combine them, y will disappear. So that's what you see here. You have x, y, z. So you can take x is common. So note that x is common between these two terms. And you also note that z is common between them, which we also see, 0, 1 and 1, 1. So z is common here. And therefore, when you combine them together, so whatever is common remains, because you will take it out, and whatever is different will disappear through the principle that z plus z bar will be equal to 1 here. So when you encircle them together, these two terms here, they combine into a simpler term, which is x times z here. X here and z, because z is common again between these two terms here. And it's for that reason, note that after 0, 1, we have not put 1, 0. Because if we had done 0, 1 and 1, 0, the two neighboring boxes would have differed in 2 positions. And so factoring would not have been possible. So that's why this particular order of 1 bit change here. So fine. So these two ones are taken care of. We have xz. Can we combine this term and this term here? Can we combine this and this here? Well, x is common between them. But between yz, nothing is common. Yz is 0, 0 and yz is 1, 1. So you can't really combine this and this term here. You can only combine the neighboring terms. So what else can we combine? So note that these two terms have been combined together. Now, this term is here. We can combine this term with this term also, because we've already said that this term is not lost. When you combine them together, you can still use this particular one here, right? So you can combine them together here. So that's what we are saying. These two terms you can combine, right? X bar. So this term is x bar yz, and this here, you can combine them together, and then you get a simpler term, which is yz here. Why yz? Because when you're doing this combination here, note that y and z are remaining constant and x is changing. X is changing here, so x disappears and you're left with yz here, which you can also see if you factor out y and z, you can factor out and you will get x plus x bar. So x in one term x is 0, in another term x is 0, in another term x is 1. So that's what we mean by changing. It's changing from 0 to 1 here. So that becomes yz. So now all these ones are covered. That's the only one which is left. And here we see that we cannot combine it with anything else. There's no 1 here or 1 here. So that remains as it is here. So our simplified function becomes, this term is x bar, y bar, z bar. This one is xz, this one is yz, and that becomes our simplified function here. All right, so let's look at a few more. So here is a function. And so we have 4 minterms in our expression. So let's, we can write them up. So obviously we can see we can combine them together here. And right now you should be able to write when you combine these two terms, which is like combining these two over here, that will map onto x. And what is common is z here. Y is changing. So xz. Well, which other term can we combine? There is this one. Well, you can combine these two also. Note that, look at this particular term. This is x bar, y bar, z bar, and this is x bar, y, z bar here. So if you combine them together, which is like taking this term here, and it's like this term, it can force over to this particular part here. So this one is in the neighborhood of this particular term also. So it's like, so this one is, you can imagine if you fold it, then this becomes contiguous with this particular term here. So you can combine this and this also here. That's what we are doing here. And you can also see, if you see this term and this term, so what is the difference? Note that 0, 0 and 1, 0. So they differ in only 1 bit. And z is common between them here. Z is common and x is also common. So you can combine these two terms here. And when you combine them, well, again, what is changing disappears and what is common between these two terms remains. So common is x bar and the other thing common is z bar here. So this becomes x bar, z bar. So we have now covered all the terms. We have covered this one through this Boolean term, this term here, and we have covered these two ones by this term here. So our final function is x bar z bar, this term, and plus xz here. So note that the Kmap is helping us to visually represent the Boolean function, and it helps us, it's much easier to see which all terms we can combine to get a simpler term, that is here. All right, so what about this one? Well, we can combine these two together, obviously. They are in the neighborhood. So when you combine them together, you get xy. We can combine these two also together, and we get xy bar. Right, so we have covered all the ones that are there here. F is equal to xy bar plus xy. Right, but we can also see that these two, this represents a term and this represents a term. We can also see that we can further take x out here. We can further take x out here and y plus y bar. So what it is saying is that it's not just possible to combine two terms. You know, so you have taken x out and y plus y bar. It's also possible to combine all four terms together here. So all four terms together here. So what happens is you're taking x out, and yz is changing from yz is 0, 0, 0, 1, 1, 1, and 1, 0. So that adds up to basically equal to 1 here, right? So when you combine them together, so x is out and yz is, so, you know, if you take x out and you're left with 0, 0, 0, 1, 1, 1, and 1, 0, which means that the function is 1. The function is 1 irrespective of the value of yz. Whether yz is 0, 0, then also is 1. When yz is 0, 1, then also is 1. When it is 1, 1, then also is 1. 1, 0, then also is 1. So which means yz doesn't matter here. So f is simply equal to x here. So you can combine four ones also together here. So that's what we are showing you here. That, you know, so all four of them can be combined to result in a simplified function x here. All right, so let's look at it here. Here also note that you have all 1s here. So you can combine all of them together. All of them together. So what happens is yz will completely go out. So yz is taking all possible values. Yz is 0, 0, 0, 1, 1, 1, 1, 0. So it doesn't really matter what is yz. And so you'll be left with f equal to x bar. Well, you can combine these fours together also. So note that when you combine these pattern also, so x is changing. So x is changing, it will disappear. The other thing is y is changing. Y goes from 0 to 1 here, and z is common. So when you combine them together, you'll be left with only z. And to convince yourself, you can write down the Boolean, the min terms corresponding to this, and see that, you know, by suitably taking out the factors, try to convince yourself that this will be equal to z also here. Well, we said that these boxes are also contiguous with these boxes here. And so, you know, you can imagine, as we said, that you can fold it such that this column then comes in the neighborhood of this one. So you can combine this two, and this also here. And that will also get, again, x is changing. And when you look at it, 0, 0, and 1, 0, so y is also changing. So this will be equal to z bar. Right? So you can combine these also together. Well, what about this one? Well, we can see that we can combine this possibility is there. And so that will give us basically z bar here. Z is common, z bar is common to both of them. So that gives us z bar. But we also have to cover all the ones. Okay, so we can also combine these here. Note that even though this one has been taken by this combination, it is still available for other terms. So we can combine them here also. And this gives us x. So the final function is x plus z bar. Right, so, all right. Can we do this? Well, the answer is no. Note that each encirclement should represent a single product term. So when you encircle them, it's a single term. Now, you know, we cannot combine 0, 0, 0, 1, and 1, 1. We cannot combine them together. We can combine 0, 0, and 0, 1 because they differ in one bit and will result in a simpler term. But three terms like this, you cannot combine. You cannot combine into a single term, which is a product of the variables that are there here. Okay. So, you can try it out and see that if you try to combine them, you're not able to get a single term, right? So that combination is not possible. We cannot make groups of 3 terms. So we have said that there's a reason why we write 0, 0, 0, 1 and 1, 1 here and not 1, 0 here, because then when you have 1, 0 and 1, 1, then what is happening is 0, 1 and 1, 0, they differ in more than 1 bit. So we cannot just combine them together, right? If we try to combine 1 and 1, we can't combine them together here, right? It's only when things differ in 1 bit that we can encircle and combine them. So that's why we write it in a particular order here. Okay. All right, so fine. So that point is there. So let's look at 4 variable minimization here. Okay, so we have 0, 0, wx, yz, 0, 0, 0, 1, again 1, 1, 1, 0, 0, 0, 0, 1. So let's say the truth table has been mapped onto the Kmap shown here. And we have to do the minimization. All right, so how do we minimize? Well, we look for ways of combining terms here. So we could combine these two together here. There are various places you can start in the Kmap. So we see that we can combine. So the idea is to cover each one of those ones that are there. You have to cover it with a term. A term is a circled, a combination, a circled term. You have to cover it, each one in as simple a manner as possible, and you would like to have as few terms as possible here. So let's cover this by this here. Okay, so this becomes w bar x, y, x, z here, so that's fine. We can cover them to, this one is also, we would like to cover. So we would like to cover this one, and so we would like to cover it with the simplest possible term, so we combine it with this one here. And so that becomes the simplest way of covering this one here. Now we are left with, fine, so we can write this out. Well, we can cover these two together here. Fine, so we get this one here. Now we are left with this one here and this one here. So what do we do? So finally we write this out in this particular manner here. And so note that these two ones have been simply written out right now. It appears as if we cannot combine, but note that this one is adjacent to this one here. We said you can fold it because note that these two boxes differ in only 1 bit. Similarly, this one and this one are adjacent to each other. You can fold it in a vertical manner here, because note that these two boxes also differ in only 1 bit here. This one here and this one here, because what is common is 0, 0, both of them, and here is 0, 0 and here is 1, 0. So only 1 bit change here. Right, so we can combine them together. Okay, so let's these two terms can also be combined. So there are various ways in which you could approach. For example, that's what we are saying. So this and this one can also be combined together. Right, so the first term, note that you can write it out, is wx, y bar, z bar. This one is wx, y, z bar, and it can be combined together. So what is common between them? Wx is wx here, 1, 1. And what is common is 0, 0, 1, 0. So what is common is z bar here. So we can combine them together. They are also adjacent to each other. So the adjacent terms can be combined. Similarly, note that these two also can be combined. You can write down the expression for this and write down the expression for this here. And you can see that you can combine these also. So what is common is yz, which is y bar, z bar. Y bar, z bar, and the other thing which is common is between wx and 1, 0 is this 0 term here, so x bar. Right, so finally that function that we had, so we combine this one, we combine this one, and we combine this one here. So now this one was left and this one was left, so we can combine here and we can combine. So this will give this term here, and we can combine these two, and that will give us this particular term. So the final function is add up each one of those terms that are there, each one of those. So we have covered all the ones in as simple a manner as possible. Simple means with as large a circle as possible here. Okay, and note that each circle represents a simple term. as compared to the individual box itself. Is this the best that we can do? Is it possible to get even a simpler representation? Well, so the idea is that, note that we've covered all of them, all the ones here, but is this the minimum one here? So note that you would like to cover each one with as simple a term as possible, and at the same time you should have as few terms as possible here, right? So let's look at a different way of doing it. So this is what we did here. This is how we covered all the ones that were there here, but let's look at a different way of doing it. So we cover these two ones here. So note that there is no possibility of covering this one except through this encirclement, so that's fine. There's no other possibility of covering this one except by combining it in as simple a manner as possible, so that's also fine. So now we could, so if I focus on this one, this can be covered in the simplest possible manner by combining with this. So in this way both of them get covered here. Now we are left with this, so this can be covered in this way here. And so this one was, we were also able to cover all the ones and give this expression here. This one also gives us an expression here. Note that the number of terms here is 4, the number of terms here is 5. So what we are saying is that you should try to cover the ones that are there with as few terms as possible and as simple a term as possible. So both of these goals are there. As few terms as possible because each term will represent a gate, and as few terms as possible because this will represent, for example, is an AND gate with 3 variables here, right? So you would like to get as simple a term as possible. So when you're combining the terms here together, you're trying to get a term which is simpler. It has less number of variables, and also you're reducing the number of terms. So one has to carefully cover all the ones that are there such that we get minimum number of terms and the terms are also as simple as possible here. So let's look at this 4 variable minimization. How do we cover it? Okay, so we could start by, let's say, taking this one here. This one here, the only way of covering this particular one in as simple a manner as possible is by combining with, let's say, with this particular one here. All right, so now when we combine it, both these ones are taken care of. Now let's focus on this one here, let's say. You focus on this one, and the only way of covering this particular one is by combining it with this here. So now we are left with only this one here. So now you would like to cover this one in as simple a manner as possible. So you could combine it like this, and also the other possibilities, not just like this here, you could combine it with this also. This particular one with this particular one here. So both are same in terms of complexity. So both of them require 3 terms and each term has 3 literals. And so both of them are equivalent in the sense of complexity. All right, so in these cases, let's look at the possibilities here. So note that we should not just look for groups of 2, but we should also see whether we can get groups of 4. So we can get a group of 4 here. So this one, what will it be? YZ will doesn't matter. YZ will go out and we'll be left with W bar X here. And we also see that the remaining ones are, we can also cover it with this group of 4 here, right? And so that becomes basically equal to Y bar Z here. So our function then becomes a sum of these two. What about this one? So, well, you should look for all possible groups of 4. So you can get a group of 4 here. And that's equal to, note that what is common between here and here is X. And what is common between here and here is basically Z. So this whole term represents XZ here. There's another group of 4 that we can get is here. And that one can be written as W dot Z here. So my function then becomes XZ plus WZ here. All right, what about this one? Well, note that these terms, that's what we are saying, these terms are also adjacent to these terms here. So we could combine these two together here. So that's a group of 4. And what is common between these two? All overall, note that 0, 1 and 1, 1. So common is x here, and 0, 0 and 1, 0. So what is common is z bar here. Well, what about this one? We can combine these two here. These two here. These are, so the terms on the top are adjacent to terms on the bottom. The term on the left-hand column is adjacent to the term on the right-hand column. Adjacent in the sense that note that 0, 0 and 1, 0 differ in only 1 bit. So you can combine them. The principle is that there should be 1 bit change, and then you can combine the terms together. So in that sense, 0, 0 and 1, 0 in these columns, they can be combined. What about here? Well, note that you can combine this one, and this one, and this one together. And you're left with basically whatever is common between them. You can write down x bar z here. Can you combine these together? Well, think about it. There are also groups of 8. So groups of 4 and groups of 8 here. We can combine all of them together here. So note that when we take all these ones together, wx goes 0, 0, 0, 1, 1, 1, 1, 0, which means that the function is 1 irrespective of the value of w and x, wx 0, 0, 0, 1. So wx doesn't matter here. So wx goes out. And between these two columns, the only thing that is common is z here. So the whole thing can be combined and equal to z. I would suggest that you write down the expression for each and see that combination is resulting into this particular value here. Well, so this is a group of 8. This is another group of 8 here. So here yz factors out, and what is common is only x here. So that's x here. Well, there's another group of 8 here. There's a group of 8 here. And so wx again goes out, and you're left with z bar. There's another group of 8 here. This one and this one here. Right? So yz goes out. Yz doesn't matter at all. And what is common between this is wx is 0, 0. This is 1, 0. So what is common is x with a bar here because it's 0. So it's x bar. Right. So these are the things that we can use for simplifying our function here. So what about this one? Well, so focus on this one here. So this one, so the idea is you have to cover all the ones with as simple and as few terms as possible. So if we look at this one, we have to cover this one, and so the only possibility is this term cannot be combined. If you scan the so that's the power of Kmap. You have to visually look at it and see can we combine this one with any other term, and we see the only possibility is with this one. So we combine them together. All right, so if we look at this one, well, we can combine it like this here. And now we are left with the remaining terms. We can combine them in this particular manner. Okay, so we'll get 3 terms and we can write these out what they are. What about this one? Well, this one, we combine them together. And what else? This one, we combine them together here. What are the other possibilities? This one, we combine them together here. And we are left with this one here. Can it be combined? Well, it can be combined with so you have to try and see what is the largest encirclement with which you can cover a particular one. Because the largest encirclement is the simplest possible term that will cover this particular one here. Okay. All right. So now let's introduce a concept which is called a don't care term here. So this is what we call as a circuit. Just to illustrate what this concept is, consider a following circuit which is called a decimal encoder. So decimal encoder is you have a binary number here. A, B, C, D is a binary number here. And you have to, it's being encoded into 10 bits here. And so the binary number is, if it is 000, then only the y0 will be equal to 0, or y0 will be equal to 1. And so you're using 10 bits to encode 4 bits here. Okay, so it's called a decimal decoder here. And so let's see. So if you have a number 001, it means that the value of this particular number is 1, so only y1 is 1. If you have 0010, so the value of this particular number is 2, so only the second bit is 1, all others are 0. And then 0011, so only the y3, so only this part is 1 here. And like that, 1001 is 9 here, so the 9th bit is 1 here. Okay, and so that's called a so if you have a number, binary number here which ranges from 000 to 9 here, so 0 to 9, and that's being encoded in these 9 bits here. Okay, so why we are doing it and all that, let's not get into it. So let's say this is the functional relationship that we're getting. If this, so the idea is if this number is 8, then the 8th bit is 1 and all other bits are 0. If the number is 7, the 7th bit is 1. Okay, and if the number is 0, the 0th, this particular bit is this thing. Now if this particular number is for example 10, well, we don't really care what happens here. We are not really interested because it's only a decimal encoder. All we are interested in is that binary numbers from 0 to 9 are encoded in these number of bits. Anything larger than that, we don't really care. So for example, if it is 1010, let's say for ABCD happens to be 1010, well, we don't really care what happens here. Y0 could be 0 1. So don't care means it doesn't really matter for my system whether y0 is 0 1 and all that, so it could be anything. Similarly, if it is 1011, I don't care, it could be anything. So we don't care state is represented by X here. So it could be 0, it could be 1, it's up to you. Whatever you give, it doesn't really matter for my system. What matters is for my system is that when inputs are from 000 to 9 here, then my system should work properly. Only one of the bits should be 1 and all others should be 0. Beyond that, for other inputs, I don't really care what happens at the output. So what we are saying is from the description of the system, you may find that for certain combination of inputs, you don't really care whether the output should be 0 or 1. And then we say that's a don't care state. Okay. So this function here, so we have a truth table, and the truth table, we can represent it by ABs, we write it here, and CDs here, right? So all 16 values are shown here. Now for from 0 to 9 here, we know, for example, if we are writing y3, so we have to generate the output y3. So for y3 here, we can write down when is y3 equal to, basically equal to 1 here. So y3 is all 0 all the time, except when CD is 1 1 here. Okay, when this is 0 0 1 1. So 0 0 1 1 here. So only then y3 is 1. The y3 output here is 1 here. For all other combinations of A, B, C, D up to 9, it is 0. Beyond that 9, when it is 10 and 11 and 12 and all that, it is all XX. Don't care here. Okay. So that's the nature of the function here. So what we are saying is that sometimes when you capture the description of a system, it may not be that the output is defined for all possible combinations of inputs. It may be that for certain combinations of inputs, you don't really care. The system doesn't really care whether it is 0 or 1. So we represent this as X here. So that's what is called as a don't care term here. Now, when you're designing a circuit, don't care, you can make these terms 0 or 1 if it is advantageous for you. If it helps in simplification, you can convert an X into a 0 or 1 also. Okay. So for example, if I forget about the don't care states and I try to write a Boolean expression, then we see that there is no other one, so we cannot combine it, and therefore our Boolean expression would be A bar, B bar, and CD. But what we can do is the don't care terms is, because of its name itself, it could be 0 or 1. So if I look at this X here, This x and this, we could combine them together. I could take this as x is 1, and because it's don't care, and therefore there's a possibility of combining together, and therefore I get a simpler term here. So don't care terms that are there should be included in this encirclement if it helps in obtaining a larger grouping or smaller number of groupings here. Now you may be thinking, why don't we convert this x's into 1? Well, if you convert them this x into 1, then you will get another term. But then that would complicate things here. So remember, the goal is to cover all the ones. The goal is not to cover x, the goal is not to cover 0, but all the ones that are there in your on your Kmap, with as few terms as possible and with as simple terms as possible. So we would like to cover this one and with as simple a term as possible, so as large an encirclement as possible. So we see that this one and this x, if we make it as 1, then they can be combined together. So don't care states can also be there in your Boolean function, and they can be taken advantage of in the simplification process here. All right, so we've been talking about simplification using basically focusing on the ones that are there, and that's when we try to conceptualize the Boolean expression as the sum of products. But we've also said that instead of looking at ones, you could also focus on 0. And so, for example, if we focus on 1, well, then we would combine this and we would combine this, and we will get a function which is the first encirclement is x, the second one is y, so we get x plus y. Well, we could focus on the 0 only. And instead of writing this one, so we could write this as, note that x is 0 and y is 0. So if we write it on, if we focus on 0 and we write it as a max term, as a product of sum, so we write this particular term as simply x plus y. So your function is x plus y by looking at 0. When does a function become 0? Well, when x is 0 and y is 0. And so we write it as x plus y here. So when x is 0 and y is 0, f is equal to 0. For all others, f is equal to 1. So we can write it like this here. So instead of working so hard by combining this one with this one and this one with this one and then writing it, well, it's because there's only one 0 here and there are 3 ones here, it's better to focus on the 0 and write down what the function is. All right, so for example, in this case, well, there are, if you focus on 0, you could combine these two together here. So when you combine these two together here, the x will go away and you have only y left here, and y is 0, so you simply write it f equal to y. Okay, so this is in the product of sum terms here. Product of sum terms here. So focusing on 0, well, you combine them together, x goes away, so f is equal to y bar. Well, if you look at here, you combine these two together here, these zeros here, and y will go away, x is 1, so but then you write it as f equal to x bar here. And in this case, these two zeros can combine together, this 0 is here, and if you combine them together, this one is x bar here, and if you combine them together here, this one is x bar here, and if you combine them together, then you get x plus, this one, if you combine them together, so this is x bar and z here, and if you combine them together, then you get x is 0 here, so it becomes x, you write it as x plus z bar here, right? So what is common is 1, and 1, when z is 1, is written as z bar here. So overall expression is product of these sum terms here. So x bar plus z and x plus z bar here. So it's just complementary. Instead of focusing on ones, you could focus on 0 and then get a representation in the product of sum form. So depending on the nature of the problem, sum of product may be of interest to us, or a product of sum may be of interest to us, and Kmap can be applied equally to each one of them here. All right, so for example, in this case, again focusing on zeros, so we can combine these two together. We could combine these two together here, the zeros and together. Well, this 0 can be covered here, and then this can be covered here. And this one is, note that when you combine these two together, what is common is y and z, so you write y plus z here, and the other thing is x, which is 0 here. So right, so you write x plus y plus z, so that becomes this one here. This one, well, y and z are y bar z bar, because both y and z are 1, so you rewrite it as y bar and z bar. And the other thing is x, 0 value is common to both of them, so we write x here. And similarly we can write these terms here. Okay, so we can finally write down, combine all these terms together as a product term here. And so the whole function can be written in this particular form here. All right, so in this case, obtain the minimized product of sum by suitably using don't care terms here. So when we say product of sum, so we are focusing on zeros. So we could combine this 0 with this one, so it would help us. So the idea here is to cover all the zeros. So we can combine these two together and we'll get a simpler term. We have another 0 here and we would like to combine it with something here. So we could combine, well, we have another 0, so we could combine it with here. Fine. And we could also combine it like this here, right? With this x here. So this 0 we can cover by combining with a larger one here. Okay, so we get each one of them, we can write it down and we'll get this final value here. Okay, so as a summary, so what in this combinational or in this digital system design, we are starting with the system description. We are capturing the truth table, and from truth table we are getting a Boolean expression, and we are getting a minimized Boolean expression, and then implementing using a gate net list here. All right, so let's stop here.